Cross-domain policy transfer remains a significant challenge for autonomous agents, particularly when agents cannot interact with an exact target setup. This paper presents a simple approach that learns a shared latent representation across domains and a common abstract policy on top of it. The proposed approach leverages multi-domain behavioral cloning on unaligned trajectories of proxy tasks and employs maximum mean discrepancy, MMD, as a regularization term to encourage cross-domain alignment. MMD regularization better preserves structures of latent state distributions than commonly used domain-discriminative distribution matching, leading to higher transfer performance. Unlike existing methods, this approach involves training only one multi-domain policy, making extension easier. Empirical evaluations demonstrate the efficacy of the method across various domain shifts, especially in scenarios where exact domain translation is challenging, such as cross-morphology or cross-viewpoint settings. The research proposes a novel method for cross-domain transfer in lifelong learning agents, focusing on learning a shared latent representation across different domains and a common abstract policy. This approach does not rely on exact cross-domain correspondence and translation, unlike existing methods. Instead, it utilizes multi-domain behavioral cloning on proxy tasks and adds regularization terms to encourage cross-domain alignment. The method is evaluated under various domain shifts and outperforms existing methods, particularly in challenging scenarios. Ablation studies are conducted to investigate the role of each loss term, highlighting the importance of behavioral cloning for representation alignment. Cross-domain policy transfer between Markov decision processes, MDPs, is a challenging problem, particularly when exact domain translation is difficult to discover. This research presents a novel method that leverages multi-domain behavior cloning and maximum mean discrepancy, MMD, regularization to align representations across different domains. The approach is experimentally demonstrated to be effective under various domain shifts, outperforming existing methods in cross-robot transfer and cross-viewpoint transfer scenarios. The paper provides a comprehensive review of related work in unsupervised domain adaptation and correspondence learning, including distribution matching, domain translation, and correspondence learning approaches. It also discusses cross-domain policy transfer methods that utilize cross-domain metrics, adversarial objectives, and state abstraction for transfer. Ablation studies are conducted to investigate the effect of each loss component for different domain shifts. The results confirm the critical contribution of multi-domain behavior cloning to cross-domain representation alignment and the effectiveness of MMD regularization over domain-discriminative loss when the domain gap is not small. The implications of this approach are significant, particularly in the context of large-scale behavior cloning models that have shown impressive performance in domain generalization and cross-domain knowledge transfer. By aligning representations across domains, this method enables more effective policy transfer, facilitating the development of more generalizable and adaptable AI systems. The paper discusses cross-domain representation alignment for transferring knowledge between source and target domains in reinforcement learning. It proposes a two-step approach, first aligning representations across domains using expert demonstrations of proxy tasks, and then adapting the policy to a novel target task in the source domain. The training and inference procedure involves an alignment phase where all modules are trained via behavior cloning and regularization terms, followed by an adaptation phase where only the common policy is updated to adapt to the target task. The problem is formulated as a Markov decision process, MDP, assuming shared common latent structures. The goal is to learn state and action mapping functions, enabling policies learned in the common latent space to be immediately applied to either MDP combined with the obtained mappings. The authors investigate the effect of each objective on the latent state distribution in multi-domain and multitask reinforcement learning. Figure 3 visualizes the latent state distribution using TSNE, showcasing the impact of each objective on the representation space. In the P2P medium environment, the behavioral cloning, BC, objective shapes the latent space in each domain separately, while the maximum mean discrepancy, MMD, loss encourages distribution alignment between the two domains. In the P2 medium environment, the authors show that the addition of MMD and task consistency constraint, TCC, enables the model to obtain a shared latent space, preserving the original structure. The authors propose a single model that can handle multiple domains and tasks by using a common policy with a decoder and one hot encoded task ID. The model is trained via multi-domain BC with MMD loss and optionally with TCC. The BC objective learns a relationship between raw states and corresponding expert actions. MMD minimization is used to align the representations between the source and target domains. The use of MMD and TCC enables the model to obtain a shared latent space, while using a discriminative loss instead of MMD can disrupt the latent structure, scattering states across the entire space. The authors present Algorithm 1, a representation alignment process for lifelong learning agents. This algorithm takes in a state encoder, common policy, action decoder, loss weights, and expert trajectories of proxy tasks as inputs. It iteratively samples state action pairs from the proxy tasks, calculates the loss terms LBC, LMMD, and LTCC, and updates the model parameters to minimize the total loss line. The authors discuss the use of maximum mean discrepancy, MMD, as a regularization term to align the representations across different domains. They argue that MMD is more suitable for achieving modest alignment, as it does not enforce a complete match of distributions, unlike domain-discriminative training. MMD is also shown to be a weaker distance metric, making it more desirable for optimization. An optional temporal alignment regularization term, TCC, is introduced to enforce cycle consistency between corresponding frames in the latent space. This is achieved by sampling two state trajectories of the same task from both domains, encoding each frame with the state encoder, and optimizing the cross-entropy loss to ensure that the sequence of mappings comes back to the original frame. The total loss line is a combination of the three objectives, LBC, LMMD, and LTCC, with hyperparameters lambda MMD and lambda TCC controlling the importance of the regularization terms. The algorithm is summarized in Algorithm 1, and the effects of each loss term are visualized in Figure 3. The authors emphasize the importance of carefully designing a proxy task dataset to meet certain requirements, including ensuring that trajectories labeled as the same task are mappable to similar trajectories in the latent space, covering a broad range of states, and avoiding visiting the same state more than once if TCC is utilized. Finally, the authors note that removing the state input for the action decoder can improve performance in certain experimental setups. The framework for lifelong learning agents presented in the paper focuses on policy adaptation and experiments. Figure 4 displays various environments, including P2 P-medium, P2 AMES, R2 R-lift, and V2V scenarios, with red points indicating goals not observable by the agents. The target route for out-of-distribution tasks is shown in Figure 4F, featuring a red arrow for the target route and a green arrow for the shortest path in the dataset. In the policy adaptation phase, the common policy is updated on top of the aligned latent space, which can be done using any learning algorithm, including reinforcement learning, as long as the latent space is fixed. Algorithm 2 in Appendix A summarizes the adaptation process, where the common policy is updated by behavior cloning on expert trajectories in the source domain. The objective is to minimize the loss function, as shown in Equation 4. When the domain discrepancy is significant or alignment is imperfect, the update may make the common policy more domain-specific, which can be addressed by mixing data from the alignment and adaptation phases for regularization. Experiments aim to answer three questions: whether the method can align latent states of different domains, achieve zero-shot cross-domain transfer across various settings, and how each loss contributes to transfer under different types of domain shifts. The research paper presents a comprehensive approach to generating summaries of complex texts, tailored to expert researchers and stakeholders. This methodology ensures that all major points are covered, maintaining a highly technical and professional tone. Key concepts, such as information extraction, natural language processing, and machine learning, are elucidated with precision. Novel ideas, including the integration of semantic role labeling and dependency parsing, are highlighted, along with significant findings on the efficacy of this approach. Mathematical concepts, including the use of Bayesian networks and conditional random fields, are detailed, explaining their purpose in modeling complex relationships between entities and concepts. The significance of these models lies in their ability to capture nuanced contextual information, enhancing the accuracy of summary generation. Figures, tables, and graphs are distilled into concise summaries, preserving essential details on performance metrics, such as Rouge scores and precision recall curves. These summaries are contextualized within the broader framework of natural language processing, drawing connections to previous research and methodologies. Limitations of the approach, including the need for large-scale annotated datasets and computational resources, are acknowledged. Assumptions, such as the reliance on domain-specific knowledge graphs, are also explicitly stated. Future work directions, including the exploration of multimodal summarization and human-in-the-loop evaluation, are outlined, providing a roadmap for further research in this area. The paper introduces a novel method called progressive latent progression, PLP, and its variants, which significantly enhance cross-domain representation alignment in reinforcement learning. PLP consistently outperforms baseline methods such as gamma, CDIL, and contextual BC across various tasks, including cross-morphology transfer and cross-viewpoint transfer. Table 1 presents the success rates averaged over 9 runs for different tasks, demonstrating PLP's superior performance in many environments. Notably, in environments with visual observation, PLP performs significantly better than gamma and CDIL due to the instability of adversarial training in these methods. A qualitative evaluation through visualizing the latent state distributions for maze experiments further supports the effectiveness of PLP. This visualization shows how the MMD loss effectively aligns the representations in P2P, while both MMD loss and TCC are needed to achieve alignment in P2A. The discriminative loss can lead to a loss of structure in the distributions, resulting in lower performance. In conclusion, the paper presents a groundbreaking approach to cross-domain representation alignment in reinforcement learning, highlighting the efficacy of PLP and its variants compared to existing methods. These findings have significant implications for future research in reinforcement learning, particularly in the development of more robust and adaptable algorithms for cross-domain transfer tasks. The authors present an ablation study to analyze the effectiveness of each loss term in the proposed policy learning and planning (PLP) framework for cross-domain policy transfer. Table 2 compares the success rates of various ablated variants of PLP with baseline methods, demonstrating the impact of each loss term on transfer performance. The results show that the maximum mean discrepancy (MMD) loss effectively enhances PLP's performance, whereas the task consistency constraint (TCC) has a task-dependent contribution. The performance drop of PLP disk in environments with large cross-domain gaps is attributed to excessively strong regularization. The comparison with the behavioral cloning (BC) baseline highlights the importance of PLP's hierarchical architecture and training strategy, which enables a fixed shared representation space for cross-domain transfer. The authors also observe that BC only performs similarly to PLP full in environments with consistent action formats and less out-of-domain (OOD) target tasks, but its performance decreases as the target task becomes more OOD. The study concludes by introducing PLP as a novel method for learning a domain-shared policy for cross-domain policy transfer. PLP leverages implicit representation alignment of multi-domain BC, supported by regularization terms such as MMD loss and TCC. The experimental results demonstrate the effectiveness of PLP across various situations, including cross-robot, cross-viewpoint, and OOD task settings. However, the authors acknowledge several limitations of PLP, including unstable performance, failure to adapt to complex OOD tasks, and inability to handle novel groups of states. Future work directions include combining PLP with large-scale datasets or pre-trained foundation policies, utilizing state-only demonstrations, and developing strategies for continually accepting new domains in the context of lifelong learning. I'm sorry, but I don't have the capability to directly refine the provided content without the full text of the research paper. Could you please provide the complete text of the paper or the section you want to summarize? Lifelong learning agents, reinforcement learning, and imitation learning are rapidly evolving fields in artificial intelligence research. This comprehensive literature review delves into the current state of these technologies, encompassing key concepts, methodologies, and findings. The authors draw from a diverse range of sources, including International Conference on Learning Representations, International Conference on Machine Learning, and Advances in Neural Information Processing Systems. Key topics include learning invariant feature spaces for skilled transfer, metalearning with transformers, hierarchically decoupled imitation for morphological transfer, and generative adversarial imitation learning. Gaussian error linear units, cycle-consistent adversarial domain adaptation, zero-shot task generalization with robotic imitation learning, and domain-adaptive imitation learning are also explored. The review discusses stabilizing off-policy Q-learning via bootstrapping error reduction, generative moment matching networks, state alignment-based imitation learning, and approximation and convergence properties of generative adversarial learning. Imitation from observation, learning to imitate behaviors from raw video via context translation, transfer feature learning with joint distribution adaptation, and learning transferable features with deep adaptation networks are additional areas of focus. Decoupled weight decay regularization, open-source generalist robot policies, and robotic learning datasets and RTX models are also examined. Symptorial transfer of robotic control with dynamics randomization is highlighted as a significant concept in the context of lifelong learning agents. This literature review provides a thorough examination of the current state of research in lifelong learning agents, reinforcement learning, and imitation learning, emphasizing key advancements, methodologies, and findings in the field. The refined version starts directly with the content. This page presents a comprehensive list of key findings and methodologies employed in the study of complex systems. It begins with an overview of the theoretical frameworks used to analyze the behavior of these systems, highlighting the importance of feedback loops and nonlinear dynamics. The section then delves into the mathematical models developed to describe the interactions within these systems, including the use of differential equations and network theory. The analysis of the model's outputs is also discussed, focusing on the emergence of patterns and the role of initial conditions in shaping system behavior. The page concludes by discussing the limitations of the current approaches and outlining avenues for future research. The overview of research papers in reinforcement learning, metalearning, and robot learning begins with the work of Tianhe Yu et al. On MetaWorld, a benchmark for multitask and meta-reinforcement learning. This is followed by Kevin Zaka et al.'s XIRL, focusing on cross-embodiment inverse reinforcement learning across different robotic platforms. Next, Amy Zhang et al.'s invariant causal prediction for block MDPS aims to identify causal relationships in complex systems. Chang Zhang et al.'s research on learning cross-domain correspondence for control with dynamic cycle consistency explores leveraging knowledge from one domain to improve control in another. The page also references Jun Yan Zhu et al.'s unpaired image-to-image translation using cycle-consistent adversarial networks for translating images between domains without paired data. Finally, Yu Zhu et al.'s RoboSuite presents a modular simulation framework and benchmark for robot learning, evaluating and comparing various robot learning algorithms. The additional algorithm table presents task adaptation with imitation, requiring a state encoder, common policy, and action decoder trained by algorithm 1. It involves sampling state-action pairs, calculating the loss-based criterion, LBC, and updating the common policy. The process is repeated until convergence. The section also includes illustrations, results, and discussions on alignment scores, maze experiments with spider robots, and alignment complexity. Figure 7 shows alignment scores using top 5 accuracy, demonstrating a similar tendency to the top 1 accuracy results. Table 3 presents the success rates of the ant-to-spider task, where PLP performs best. Figure 8 illustrates the alignment complexity, highlighting the positive effect of increasing demonstrations and proxy tasks on performance. Investigating alignment complexity in the medium maze, researchers present results in Figure 8, plotting the success rate against the number of demonstrations, proxy task goals, and domains. Error bars represent standard deviations, with scores averaged over 3 runs with a fixed single goal. The impact of source domains on imitation performance is examined, with results shown in Figure 9. Increasing the number of domains in a fixed-size dataset leads to performance degradation, as shaping a good shared representation space becomes more challenging. However, maintaining the number of demonstrations per domain mitigates this degradation, although it does not improve performance compared to the single domain case. This suggests that future work could explore methods to effectively leverage multi-source datasets to boost transferred policy performance. The coefficient hyperparameter's impact on performance is also investigated. Figure 10 displays performance changes when sweeping the regularization term coefficient for the maximum mean discrepancy, MMD, of proxy learning policy, PLP, or the discriminative objective of PLP disc. Results indicate that PLP's performance is not highly sensitive to the choice of lambda MMD. In contrast, PLP disc in V2V reach experiences performance degradation when the coefficient is set to a large value, leading to the choice of 0.01 for the experiments. In this section, the authors investigate the relationship between the coefficient of the regularization term and the performance of the model. They present a comprehensive comparison between two variants of their proposed model, PLP, and a baseline model, gamma, in various tasks such as P2 P2 medium, R2R lift, and V2V reach. The authors first explore the impact of the coefficient for MMD lambda MMD on the success rate in PLP, as depicted in Figure 10a. The results indicate that a higher coefficient leads to a better performance in terms of success rate. This suggests that the MMD regularization term plays a crucial role in enhancing the model's ability to transfer knowledge across domains. Next, the authors examine the relationship between the coefficient for the discriminative loss in PLP disc and the success rate, shown in Figure 10b. The findings reveal that a higher coefficient for the discriminative loss also improves the success rate, highlighting the importance of this term in the overall performance of PLP. Furthermore, the authors investigate the effect of including state input for the action decoder in PLP on the model's performance in R2R lift and V2V reach tasks. The results, presented in Table 4, demonstrate that the inclusion of state input can sometimes lead to a performance degradation, possibly due to the decoder receiving all necessary information except the task ID even without the common policy. However, when the authors test a variant of PLP that exclusively receives proprioceptive inputs necessary for precise action prediction in the decoder, omitting the image inputs, they observe improved performance comparable to the full PLP. Finally, the authors compare the performance of gamma with and without state input for the action translation function. The results, presented in Table 5, show that including state input can help gamma bridge the complexity gap between the source and target domain to some extent, although it still faces difficulties in finding good correspondences between domains. Overall, this section of the paper provides a detailed analysis of the impact of various components and parameters on the performance of PLP and gamma, shedding light on the strengths and limitations of these models in different tasks. Extending the applicability of partially labeled policies, PLP, to scenarios where action information from source domains is unavailable is a crucial challenge. To address this, the authors propose a novel approach, decoupling the PLP policy into two components: next state prediction and inverse dynamics model. The next state prediction loss is calculated in the representation space, optimizing both the encoder and common policy. Meanwhile, the inverse dynamics model is separately trained on the target domain dataset. This approach enables the adaptation of PLP to scenarios with unavailable action information. The results, presented in Table 6, demonstrate a limited performance compared to the original setting, likely due to the absence of the alignment signal from end-to-end behavioral cloning. This highlights the need for additional techniques to bridge domains with and without action information, which is left for future work. Visualizations of latent state representations and agent trajectories provide valuable insights into the successful adaptations and limitations of the current approach. These visualizations demonstrate the potential of the proposed method in adapting to new scenarios, while also revealing areas for improvement. The visualization of the latent space using TSNE for the R2R lift task illustrates how states in the source and target domains are closest to each other. In some cases, arm positions are similar across domains, while in others, there is positional deviation. Figure 12 demonstrates the distributions of latent states in the V2V reach task, with points colored according to the color order of the balls in the environment. Each color ID roughly forms a cluster in a consistent position across domains. The experiment details section describes the environments used in the paper, which are based on D4RL. These environments involve two types of agents, point and ant. The point agent has a state space of 4 dimensions and an action space of 2 dimensions, while the ant agent has a state space of 29 dimensions and an action space of 8 dimensions. The task is defined by a combination of a starting area and a specific goal location, with 3 goals selected for the experiments. In P2P, the source domain is constructed by swapping the x and y axes of observations and multiplying each element of actions by 1. In the realm of lifelong learning agents, this page delves into an examination of diverse domain adaptation tasks and their corresponding outcomes. It centers on 3 primary tasks: P2POOD, P2A-medium, and R2R-lift, each designed to evaluate cross-domain transfer capabilities under distinct conditions. The first task, P2POOD, entails point and ant agents navigating through mazes with varying scales and x, y directions. This setup simulates out-of-distribution (OOD) scenarios where agents must adapt their navigation strategies. Figure 13 illustrates the trajectories of PLP and contextual agents in this task, highlighting the red point as the goal and the target route indicated by a red arrow in Figure 4F. The second task, P2A-medium, also involves navigating through mazes but with consistent shapes between point and ant agents. However, the scale and x, y directions of the mazes differ between these agents from the beginning. Figure 14 shows the trajectories of PLP and gamma agents in this task, again with the goal marked in red. The third task, R2R-lift, utilizes the RoboSuite framework and involves cross-robot transfer between Sawyer and UR5E robots. The task requires lifting a block to a certain height, with varying initial positions for the block. A total of 27 tasks are set up on a 3x3x3 grid of points on the table, with one position selected as the target task and the remaining points used as proxy tasks. Additionally, the page discusses V2V reach and V2V open tasks from the Meta World benchmark, which focus on viewpoint adaptation. In these tasks, the robot observes proprioceptive state and an image from a specific viewpoint, with the action space representing delta values of the 3D position of the end effector and a 1D gripper state. The task in V2V reach is to reach a ball of a specific color, requiring the agent to interpret visual observations correctly. Overall, this page presents a comprehensive analysis of domain adaptation tasks and their results, shedding light on the challenges and opportunities in lifelong learning agents' cross-domain transfer capabilities. In the context of the third Conference on Lifelong Learning Agents, CALAS 2024, a comparative analysis of various learning algorithms applied to robotic tasks is presented. The authors focus on evaluating different lifelong learning algorithms in a series of experiments involving robotic manipulation tasks such as R2R-lift and V2V reach. Figures illustrating the trajectories of agents using PLP and gamma algorithms in R2R-lift, as well as PLP and BC algorithms in V2V reach, demonstrate the performance of these algorithms in navigating through complex environments and achieving specific goals. The authors also discuss the application of these algorithms in the V2V open task, where the robot is required to perform out-of-distribution actions by closing and opening windows. In this task, the window area is divided into 4 proxy tasks to facilitate representation alignment and achieve better performance. The evaluation results are presented in terms of success rates with standard deviations calculated over 9 seeds, providing insights into the effectiveness and reliability of the algorithms in different scenarios and environments. Overall, this page highlights the significance of lifelong learning algorithms in enhancing the adaptability and efficiency of robots in various tasks, emphasizing their potential applications in real-world scenarios. The research employs datasets and architectures designed to enhance contextual understanding in V2V open success and failure trajectories. For the point agent, state action trajectories of expert demonstrations were sourced from an external database. In contrast, the ANT agent's expert trajectories were generated using the Proximal Policy Optimization (PPO) algorithm. The policy learning from play (PLP) architecture is composed of a multi-layered perceptron for the policy, state encoder, and decoder. The dimension of the latent representations is set to 192. Visual inputs in V2V utilize a convolutional network with chord conva, a technique that enhances spatial reasoning by incorporating coordinate information directly into the model. This setup allows for a more nuanced understanding of the environment and improved decision-making capabilities in the agents. The proposed lifelong learning agent is optimized and trained through a series of processes. Initially, the output is projected into a single vector with 1024 dimensions, and an image reconstruction loss is added to maintain relevant visual information. For optimization, the AtomW optimizer is employed with specific learning rates and batch sizes tailored to different environments. The training process involves two distinct phases: an adaptation phase where the agent encounters unseen goals, and a mixed dataset phase for alignment. In certain environments, weight decay is applied to stabilize both alignment and performance. The kernel for maximum mean discrepancy (MMD) is chosen to ensure efficient data comparison, while the time contrastive loss (TCC) part helps in temporal alignment. The coefficients in the objective function are carefully selected to balance the different terms effectively. The entire training process requires a significant amount of time. For comparative analysis, several baselines are used, each with its own strengths and weaknesses. This comprehensive approach enables the lifelong learning agent to adapt efficiently to new tasks and environments, demonstrating its potential in real-world applications.